us out here at JCC on this really what turned out to be a beautiful Saturday, so I know it's a sacrifice after all the rain we've had this spring to come on out here. But before I get started, first of all, just let you know that I've been a teacher out here at JCC for about 25 years now, so this has pretty much been my whole career. And I've taught a lot of algebra in the last 25 years. And one of the things that's always interesting to me is, what can you do with algebra besides just solve equations and see it in the abstract? Where does it fit in, and where is there math hidden behind the stuff that we might see every day? So I want to give you just a little bit of a taste of that today. Now, I've already met a little bit. Now, are you guys all from Parkside up there?
Yes.
Yes?
Yeah.
All Parkside, meet your students and teacher, Mom?
I'm Mom.
Mom, all right, great. And you are from?
Jackson area, former student out here.
Okay, great. And you're a committee member or teacher?
Used to be a teacher.
Okay, great. Well, I welcome you all, and again, thanks for being here. Let's start by talking a little bit about where you might be able to see a little bit of math and also maybe use a little bit of math to construct an argument about a sports topic. I don't know if any of you guys were glued to the television last summer and watched the Olympics like I did, but I was a real big Olympics fan. It's about the only time I ever watch sports on TV is when the Olympics are on. But I did last summer. And one of the big Olympic stars that year was what they were calling the world's fastest man. Have you guys heard of Usain Bolt? Yeah? Well, there he is. He did something that had never been done before in Olympic history. He took the 100-meter sprint gold medal in 2 consecutive Olympics, 2008 and 2012. He did the same thing in the 200-meter men's sprint. One of the other really unusual things about Usain Bolt is that he's not your typical sprinter. If you guys watch sprinting at all, sprinters tend to be on the shorter side because they got to get going fast. They only have a very short time to win that race. Usain Bolt's 6'5", which is really, really tall for a sprinter. He's got a lot of inertia to get going that fast to win such a short race. So the fact that he could do that was really unusual. Here, very quickly, this one for you, is just a moment.
Bolt versus Gay. 5 years between them. One's a world champion.
Record-breaking run.
And in terms of a real challenge, I think in their time as Bolt's
And that's him in the yellow and green.
different resonance, a different time.
Thanks.
You bet. See how much bigger he looks than the
The
rest of them.
Bolt is loaded. The World 100-meter final. They're going to win first time. Tyson Gay right alongside Usain Bolt, but here he goes, streaking away already. It's Bolt all the way. He's looking round at Gay. Watch the clock. It's gone for Bolt, and again he's done it
See how much
again.
in one body in 100 meters.
New world record for Usain Bolt. They say lightning doesn't strike twice. Can you believe it? He is flying. The world belongs to Bolt. Berlin belongs to Bolt. 9.58. Stunning. Absolutely stunning. Gay was good. He was very, very good. They are adjectives which are inadequate to describe this man.
And that was his patented move there, his lightning bolt. So that's what the commentators started calling him with a history as a sprinter. To have a name like last name like Bolt, you had to have lightning for a nickname, right? So that's what they were nicknaming him. Here's the question I want to ask you guys today, and this is where we're going to bring some math into. Commentators and Bolt himself have said he is the best sprinter of all time. Now, certainly he's the best sprinter in the world today, and he does hold the world record at 9.58 seconds, which was the run you saw there, which was actually not in the Olympics. It was in 2009 at the World Championships. But when you say of all time, there have been sprinters throughout history who've done great things, right? There have been people all through history who've broken records, and they were the best sprinter in their particular moment. So what gives Usain Bolt the right to say that he really is the best sprinter of all time? Is he special? Is he better than any of the people who set those records there? I have their names actually on this if you guys want to give them these. And so what I do is I want to use a little bit of math to try and investigate whether we think that Usain Bolt's record, right? His record is actually the next one that was broken after there, 1999, the record was 9.79 seconds. In 2009, he set the record that you guys saw at 9.58 seconds. Now, as we look at what's happened through history, of course, the world record times get shorter and shorter all the time, right? So, do we think that 9.58 was just kind of what we would have expected by 2008 anyway? Or was he really something special? Did he truly shatter those world records, like the sports commentators talked about? So that's what we're going to take a look at today. In order to do that, I'm actually going to do this on a graphing calculator. I've got some spares here. If any of you guys want to follow along, if you just want to watch, that's okay too. But those of you who are technologically inclined and like to play, I've got some extras here. Go on. All right, so what we're going to do is we are going to go ahead and we're going to put in the information that's in the table that I gave you guys, and we're going to see if we can figure out whether Usain Bolt was really something special or not. I'm going to start by just, whoops, I got to turn this on, I guess. Okay. We're going to start by taking a look at the data that you guys have in front of you. And if I can zoom in a little bit on this. In order to put this information in the calculator, we're not going to use the whole year, because those are really big numbers, right? 1,921 or 1,930. Instead, what we're going to do is we're going to go ahead and we're going to talk about our time as how many years after the year 1900 it is. So instead of 1921, I'm just going to think of it as 21, right? And instead of 1930, I'll think of it as 30, and so on. Okay. Those years that I just wrote up there are the years that we're going to tell the calculator first. They're going to represent the year. Okay? So here you go. How many of you have used the TI-80 course before? Not at all? All right. You have?
I think we have.
All right.
Yeah, but
Well, then this will be an adventure. Here's what you're going to do. You're going to start by looking for the stat key right here, kind of next to the arrows, and click on that. Oh, I'm not on there. I'm sorry. I got to go back to the computer here. There we go. So click on that stat key first. And we want to edit some data. We want to put some data in there. And the number 1 here says edit. So I'm just going to go ahead and I'm going to type the number 1. And hopefully what you guys see is an L1 and an L2, but do you guys have nothing here? I tried to clear them all out, so don't do this. I got to clear these real quick. Okay. What we're going to do is we're going to put the numbers that you guys have written down in your paper, the years, 21, 30, 36, we're going to type all those into the first column right here into L1. So I'm going to type in the 21, and I'm just going to hit the enter key. And then I'm going to do the 30, and the enter. Keep on going, put them all in. All right, doing okay? Fantastic. All right, now go ahead over to the second column. Just use those little arrow keys here to move around. And in the second column, we're going to put all those world record times that you see again on your sheet, starting with the 10.4. Enter. 10.3 and enter, and so on. You guys have faster fingers than I do usually.
Oh, you're using mouse, we're using our.
Thank you, that was very kind of you, and I appreciate that. All right, you guys okay?
Yep.
Good. Not quite, we'll give you a minute, no problem.
I don't know. Okay.
All right, so here's what we're gonna do next. We want to take a look at what those points look like when we plot them. Have you guys plotted points on a graph before?
Yes.
Yeah, awesome. We're just gonna use the calculator to do that to save us some time so we don't have to go through and do it with pencil and paper, all right?
Oh, yeah.
So here we go. What I want you to click next is this y equals key. And then I want you to go up with the up arrow so that that plot 1 is highlighted. And then click
Where's
enter.
the y equals?
The y equals is up here.
Oh, okay. Then you go.
And then go up with the arrow so the plot 1 is highlighted. And then click on enter. And then use the arrow to come back down. And you should see that plot 1 still in kind of a black. Does that look okay?
No, wait.
Okay. All right. I'm almost ready to graph my points. The other thing I need to tell it though is I need to tell it how big to make the graph. You know how when you plot points by hand, you have to decide, are you going to count by 5s or 10? Do you need to go up to 50 or 1,000? All those decisions. We have to do the same thing on the calculator, and we do that here in the window. So I'm going to start by saying my first list was the years. And remember my years went from 21 to 99 on your sheet? So what I'm going to do is I'm going to tell it, let's go from 0, enter, to 100, enter. And I don't want to count by 1s, that's too many tick marks. I'm going to count by 10s. So the scale there, I'm going to tell it is 10. So it's going to go 10, 20, 30, 40, 50, and so on. Now the y values, the world record times, went from 10.4 to 9.79.
So you want 10.5?
9.5, that'd be a great place to start. Let's do that. Let's start at 9.5. And how big do you think I should make it? What should my maximum be?
11.
11 be perfect.
Wait, 9.5 and 11.
Yep, that would be a smallest and the biggest, and that would definitely cover our data. Awesome. Okay, what do you think about a scale there? Should I count by 1s?
No, you should count by 10s.
I love it, yeah. Counting by 1s, I'm only going to see 1 tick mark, right? That's not very many. So I think counting by 10s, 0.1 would be excellent. All right, now we've got it all set up. We're ready to see the points, and you do that with this graph button in the upper right-hand corner. So everybody seeing, you might be seeing little dots or you might be seeing little squares depending on the settings on your calculator. Are y'all seeing the points somehow?
Wait, what do we do now?
What's the X-res supposed to be?
Oh, you don't have to mess with that. That's just the resolution. Just leave it at 1. And then if you click on this graph button, it's up here in the upper right, you should see your points. Mine are set to little squares. Yours might be set to little dots, but you should be able to see it. You see it okay?
Yep.
Wonderful. All right, so here's the question we have for you guys. Could you imagine, for a moment, if you had a ruler, could you see that if you put a ruler in just the right spot on that graph, you could draw a line that would come pretty close to all of those points? Yeah. What we're going to try and do is use the calculator to find that line, and then we'll use that line to answer our question.
Like connect the dots.
Kind of like connect the dots, yeah, exactly. Now, when you guys take more algebra, and depending on my audience, I was going to do this one way or the other, but I'm going to do it with the calculator today. But when you guys take more algebra, you'll learn how to find the equation of this line just using a pencil and paper. That's a little more than we want to get into today, because you probably didn't really want to go to math class today anymore. So today we're going to use the calculator. We're going to use the cool technology to do it. But you will learn that from your math teachers in the next couple of years. All right, so here we go. You ready? We're going to go back to the stacked button again. And this time I want to make a calculation. Right? See where it says calc here? To get there, I'm going to use the arrow key to move over to. And I want the equation of a straight line. There's lots of different mathematical curves that we can find, but we said a straight line was pretty close to what we wanted. So we're going to go ahead and we're going to choose number 4. LIN stands for line or linear. So I'm going to type in a number 4, and then I'm going to hit the enter key. Did you guys get something that looks like that? There's a couple different operating systems out there, so I want to make sure you're all okay.
Mine is like.
Let's see what you got. Want to go ahead? Sure. You might have to hit enter a few times if some of the newer operating systems, if it just hasn't done it yet. You there? All right. So what's this telling me? This is telling me, in code, kind of, because the calculator uses code, that the equation of my line, y equals ax plus b, has an a value of about negative 0.007. So it would be y equals negative 0.007 x
Plus 10.5.
plus 10.5, exactly.
First you add, well, we just have to double, we have multiple variables.
Right, yeah. And remember, what were our x values? What was in this first column of numbers here on your page? What did we put in first?
The 1900s.
The time, yeah, the years, exactly. These are the years. And what were the outputs? What were the y values?
The time.
The record times, yeah, exactly. Okay. So what I want to do next is I want to find out from my calculator whether this line really fits pretty well. Does it come pretty close to the points? It should if the calculator did its job right. But let's see if it does. Okay. I want you to go back to that y equals key again. And this time, see how it's blinking right by where it says y1 equals? What I'm going to do is I'm going to type this equation right in there. It already gave me the y equals part. So I'm going to type the negative. And by the way, make sure you use a negative, not a minus sign. Negative's down here. So negative 0.007. Your X button is up here next to the green key. X plus 10.5. Guys got that typed in okay?
Yep.
Fantastic. Tell your calculator to graph again.
That's a pretty good.
Did a pretty decent job, didn't it?
Uh-huh.
Yeah, that line comes really close to all those points. Right. So that's one of the things that we can use math to do. We can say if we've got a set of data, we've got some points, we can use math to come up with an equation. It's what we call a model for these points. Is it perfect? Does it really go through every point like it would in connect the dots?
No.
Not quite, right? But it's pretty good. It's pretty good. So when we have a model, we can use our model to make predictions. Okay? Now, are these predictions absolutely positively going to be perfectly accurate?
No.
Probably not, right? Just like it's not perfect there. But it can give us a good idea of how we might actually make some predictions about the future. That's what we're going to do next. So I'm going to go back watch here. Okay. And I'm just going to go ahead and I'm going to say our equation was y equals negative 0.007x plus 10.5. Now, a lot of times in math, we would like to use letters that mean something to us. X and Y are kind of generic math letters, right? We use them all the time. But I might want to use something that's a little more meaningful. So what I'm going to do is I'm going to say, instead of using Y, let's let R be the record time. So I'm going to say R, the record, equals negative 0.007. And I'm going to say that the years, I'm going to say T for time, times T plus 10.5. And that's just going to help me to remember when I plug numbers in there, whether I'm plugging in numbers for the record or whether I'm plugging in numbers for the time years. All right, we're almost ready to answer the question. Just based on what we're going to do today, I'm going to go ahead and I'm going to skip number 3. I'm going to go to number 4 here. And what I want to do now is I want to make a prediction. I want to say, based on what I've learned so far, how fast do you think Usain Bolt should have been able to run when he set that record in 2009? Okay? So I'm going to look at the year 2009. Now remember my equation. It's right here. What do you think I should plug into that equation to make it the year 2009?
You should plug in 2009 and T.
In the T value, good. So the year, the T value, is 2009. But was I using the whole year? What should I use?
109.
109. Awesome. Because I started in the year 1900, right?
Mhm.
Yeah, exactly. So I'm going to say T equals 109. Perfect. Okay, so let's do that. The record should equal negative 0.007 times 109 plus 10.5.
Now we just solve it.
Exactly. So I'm going to say second quit to get back to my main home screen there. Oops, I'm not in there again. I'm sorry, I keep forgetting.
So the second mode.
Yeah, and then it was, what I did was I did the second and then this mode button for quit, and that takes me back to the screen where I can do calculations. And I'm going to type that in. Negative 0.007 times 109 plus 10.5. And that's how fast, according to the pattern that had been established for 100 years, right? Almost, we looked at data for 100 years. That's how fast we would have predicted that he should have been able to run in 2009. So what do you think? Was he justified? Were the sports writers justified in saying that he was truly an outstanding sprinter?
Mm-hmm. Yep.
Yeah. I mean, that's what, more than 1/10 of a second faster than we thought he should have been able to run? And I don't know if any of you guys have run track, but 1/10 of a second is a long time in 100-meter dash times. So, in fact, what? If you subtract the 9.58, which was Bolt's time, no, I'm glad I got you here to remind me. Usain Bolt actually ran more than 1/10 of a second, about 1600ths of a second faster than we expected. So I would say now I would defend this because he's 0.16 seconds faster than expected. And I think that's kind of one of the cool things about math is, you know, everybody has an opinion and everybody's entitled to it, but you got some weight behind your opinion when you got math on your side. All right. So let's see here. We have about 25 more minutes to kind of decide what we should do here. You think so? All right. It's more fun. All right. We'll do the M&Ms next because it's probably going to get you guys a little snack to keep you going for the next 25 minutes, and then we'll save the music for the very end, and we'll see how far we get on that. But once you get a regular, like about 3 little pockets, that should be enough.
Hey, this is maybe next week, maybe next week, we'll just work both of that on that project.
Yep. You never do. Oh, you already plugged that in. Sorry. I was worried about you tracking my participants, Jake, that you tracked
Well, I
them.
can certainly say that this is the best one because we get candy.
All right, so here's what you're gonna do. You are this time, instead of using data that I can find on the internet, and by the way, you guys can go and find out, I don't know, what are you swimmers, runners, you can find data like that on anything, right? Do you do sports? Baseball? You can find baseball records, absolutely. You can do that kind of thing that I just did, swimming records, absolutely. You can find out how much Michael Phelps beat the records by, all that kind of good stuff, right? You could do that kind of same thing that I just did with any sport. And so it's kind of an interesting way to get involved in a mathematical way with a sport that you might be interested in. We'll talk a little bit about music too in a little bit, because that's another thing a lot of students do in school. But whether you're into sports or not, whether you're into music or not, everybody's into M&Ms, right? So here we go. What we're going to do is, we're going to have you do a little experiment here. And you'll probably need to open at least 2, if not all 3 of your packages of M&Ms. All right, you guys, give them all another cup, would you? Another cup, yeah. We'll go ahead and have you start with all your M&Ms in one cup, just sort of your holding tank for M&Ms, if you will. And then we'll use the other cup as the shaker. So what I want you to do is I want you to start out by going ahead and putting all your M&Ms in one cup except for 2. I want you to take 2 M&Ms and put them in your shaking cup. The rest of them are just in your holding tank. In the situation that you have right now is what I have listed on your M&Ms page, which is what color? Blue. Blue? Thank you. Let's do the blue page. That's listed as trial 0. 0 is kind of like the beginning. And at the beginning, we have 2 M&Ms. What you're going to do is you're going to go ahead and you are going to toss your M&Ms onto the paper plate.
Like you would roll a dice.
Yeah, just like you roll dice, exactly. And if you notice, one of my M&Ms landed with the M side up, and the other one landed plain side up, right? You may have that or you may have something different. What you're going to do to do this experiment is every time you see an M side up, go to your holding tank and add another M&M to your pile. So I'm going to add 1 because I had 1 M. You have both M's, you get to add 2. You have no M's, you don't get to add any. All right? And I'm going to record this as trial 1. After trial 1, I had 3 M&Ms. Put all 3 M&Ms into your shaking cup and do it again. This time, I have 1 plain and 2 M's.
I have all 3 of them.
You have all 3? So I'm going to get to add 2. You're going to get to add 3. Every time you see an M, that's how many new M&Ms you add.
So we just continue
Just
to.
keep doing it, yeah. And every time you, don't forget to write them down. I happen to have 5 now, so I have to make sure I write that in my sheet. And once you keep doing that, see if you can get to 8 trials with the number of M&Ms you have.
ability is to get all of them and set up.
How many amounts do you have?
You don't know yet.
Okay, how many do you have right now?
Or
Then it would be 1 half times 1 half times 1 half, 11 times. So 1 half would be 11 powers and the probability of being all inside of it. Each one is a probability of 1 half, right? That's it. Good question.
yeah, and I do academic giving, so I'm kind of getting in back totals.
That's awesome. Absolutely, that's great. Are you sure? Fine, we better give you another packet, and that's all there is to it.
Okay, pretty good.
Anybody else run out?
I'm at number 8, I got 19, so do we keep doing it?
So once you've got your whole chart filled out, you can stop. And what we're going to do is we're actually going to put this new data in that calculator again. We're going to see what it looks like.
Okay, can you put these back?
I'm short 4.
You're sure, Corey? You better have another packet too. Okay. Yeah, give me another packet. And yeah, you can keep the cups too, so if you want to carry them around and snack on during the next session.
I just said the last section.
Oh, yeah.
Oh, really? All right. So everybody got your data?
Yeah.
All right. Let's go ahead and take a look at the calculator. I'm good. Here we go.
Where's Mr. Calculator?
Come on down. It's coming. Just takes a while to catch up on this. All right. You guys are pros now. You've done this once, right? We're going to put the data in again. And so this time, my first column of data is going to be the trial numbers, right? Trial numbers 0, 1, 2, 3, just like we had on our paper. So we're going to go into that stat again. And number 1, edit.
Oh, no. Oh, man.
We got extras if you
That's
saw we got
okay.
extras.
We'll leave it for the Kristi answer.
This is still a lot. This is still small. So this one goes. Put on this cover.
Okay.
Yeah, we're good. Don't worry about
Are
it.
you okay?
Yeah.
All right, awesome. Okay, so let's see. First of all, you have to get the old data out of there, and I did one already, and then I forgot you might not know how to do that. So what you want to do is, remember first it's stat, and then number 1 for edit. And then you're going to go up, and you're going to highlight where it says L1, so you have that little black square around it, and then push the clear button. And it's gonna look like nothing happens, but then if you use your arrow to come back down, it all goes away.
Disappears.
Yeah, it's kind of like sitting there behind the scenes. So do that, so your L1 and L2, so you got them all cleared out again. All
What
right?
was that step again, please? The
Sure.
clearing the L1s?
So go up and highlight L1, and then push clear, and then use your arrow to come back down into the list. Everybody's good? All right, I'm gonna put all my trial numbers, 0 through 8. And then in your list 2, yours might look different than mine. I'm gonna put my numbers that I got for my trials, but you go ahead and put the numbers that you got for your trials, okay?
Right here. That's it. Compare ours. 2, 3. You got one more. Those 2. 11, 15, 22, 23, 30, 40, you're going 35. I just want you to pick 2. We got fairly similar.
You guys okay?
Mhm.
You got them in there? Awesome, you guys are so
We all
good.
got very similar.
You know what? That's absolutely true. And you know what? We're even gonna talk for a minute about that because somebody sitting back there mentioned probability, and we're gonna talk about that before we're finished. All right, here we go. So again, I'd like to start by saying I kind of like to look at the points and see what they look like. So I'd like to plot them like I would do on graph paper, except I'm gonna use my calculator. So let's go into y equals again. And that old equation, that was all about the world record times, right? That has nothing to do with my M&Ms, so I'm gonna clear that out of there. I don't want that there anymore. Next, I'm gonna set a new window up. The first column, the trial numbers, what do you think I should put in for my x min and x max to work out good for that?
0.
0 and?
55.
Oh, you're thinking about the second column. Think about the first column, the trial numbers.
0 and 8.
0, yeah, so like if I went to 0 to 8 or 10 or something, I like to leave a little bit of space so it doesn't kind of like hang off the edge of the calculator. So I'm gonna go 0 to 10, if that's okay with you guys.
Yeah.
And counting by ones would work fine there, right? I can count by ones from 0 to 10. All right, now, as far as the number of M&Ms, that was the second column, the y's. 0's okay for a smallest number again, but now how big do we need to go?
55.
55,
We
did
didn't
I get more than that?
56.
56, 60,
57.
all right,
63.
85, should we go up to 100?
Sure.
We could. You know what, you can pick your own. Just make sure you pick a number that's at least as big or maybe a little bit bigger than the largest number of
How about we
M&Ms
just all
you
do
know.
100 because we all are on 100.
Should we go 100 so we're all the same? All right, let's do it. And I probably better not count by ones now. I probably better count by what?
5s.
5s, 10s, either one of those would work really well. Yeah, so I heard 5 first, so we'll do 5. The extras, you can just leave that again. And I'm gonna say graph. So we hit the key in the upper right. If I got my ruler out again, would you be able to find a straight line that would come pretty close to those points? Not this time, huh? That's definitely not a very good straight line pattern.
I gotta go.
It's a much more curved pattern this time.
Yeah, but mine's kind of like straight.
And then it suddenly goes up? Yeah. That's really typical of this other kind of equation that I was talking about today. The first one we talked about was the equation of a line. This is something different that you two probably haven't talked about yet, but believe me, you will. It's called an exponential equation. And have you ever heard of anybody say, oh man, that's growing exponentially? Have you ever heard anybody talk that way?
No.
No? The adults have.
Yes.
When somebody says that, what they usually mean is it's growing really fast. And what you can see is the start of that, right? It started out kind of gently going up, but then all of a sudden it kind of took off and it went up really fast. That's what we call exponential growth. And that's the pattern that we're seeing here with these M&Ms, is that at first you were only adding a couple of M&Ms each time, But then you started adding 5 and 10 and 20 M&Ms, right? And the number was going up a lot faster. So that's what we call an exponential equation. And we're lucky because the calculator knows how to do those too, just like it knows how to do lines. So go back to your stat again. And once again, I want to make a calculation now. So I'm going to use my arrow key to go over to calculate. And this time, I'm going to have to go down a ways. So I'm going to use my arrow key, and I want you guys to keep going down, keep going down. And you'll see EXP for exponential when you get down to, actually it's the 10th one, but it has a 0 in front. You find that one okay? Yeah. All right, that's the one we want. It's exponential equation, so I'm going to hit enter. And I have to hit enter again. Now my calculator says this. The equation's form is going to be a times b raised up to the x power. If I'm going to write like a normal mathematician, I would write that like this, right? With the x power like that. And they told me this time a is about 2.1. Let's call that. I'm going to do parentheses just to separate it. B is about 1.5, right? And again, you might have slightly different numbers than I do because you did your own numbers. But did you all come out with an A kind of close to 2? Anybody get a number really different than 2?
Got about 2.3.
2.3?
2.06.
Yeah, I got a 2.3.
2.3, yeah. Anybody get a number way different than 1.5 here?
I got 1.5.
1.5? 1.5?
1.59, should I round up?
Yeah, you have 1.6, that's okay. What's happening here is, on average, if your toss was perfect and the M&Ms were perfect, how many of the M&Ms each time do you think should have come up with the M sign up?
About half.
About half of them. Half is the same as what percent?
0.5.
50%, right? Or 0.5. That's what this 0.5 is right here. We keep 100%, that's the 1, of the M&Ms we had before. And then you added about 50% more. So that's why that number is 1.5 right there. It's because you're adding about half as many M&Ms as you had each time. And interestingly enough, although we all did it differently, right? We all, as you said, came up with very similar numbers in very similar equations.
What about the 2.1?
The 2.1, great question. The 2.1 actually represents what we started with. If I put trial number 0 in here, what would happen if I put in 0?
How would I sit up so
X was the trial number, right?
Oh,
So I have,
0 at the end. It would equal 1 times
oh,
2.
what equals 1?
The powers.
Yeah, anything to the 0 power equals 1, right? So this is just 1, right?
Mm-hmm.
So I have 2.1 times 1, which is 2.1. So that says that according to my equation, at trial 0, I started with 2.1 M&Ms. Did I kind of? Pretty much, right? I started with 2. So that's pretty accurate. So I guess if you all got a number pretty close to 2 there, you should have. Because that really does end up representing how much you started with. All right, now again, this one was just for fun. But just to kind of explore a little bit the kinds of questions that you can answer this way. Although you ran out of M&Ms, if I now asked you a question like D here, could you predict for me if you had enough M&Ms, how many you would have had if you did 12 trials?
Probably about, let's do the equation first. 150.
He's guessing 150? Let's try the equation and see if he's right, okay?
12 times 15 is...
My equation was y equals 2.1 times 1.5 to the x. If I'm going to use that equation to see if your 150 is pretty close, what should I put into that equation?
12.
12 for the x value, right? Yeah. So let's see here. You just do it in your calc, well, actually. Go. Again, I'm going to do second quit. And I'm just taking it back to my home screen clear in case you were in the graph or anything. And I'm going to say, what is 2.1 times 1.5 raised to the, notice that's that little caret key there, raised up to the 12th power. Ooh, pretty big, huh? You'd expect somewhere around 272 M&Ms by that 12th trial, which is way more than I gave you today.
Well,
Okay. There again, that's that idea of exponential growth. It grows fast. Faster and faster all the time, in fact. And that's an exponential equation. All right. Am I shining? Okay. All right. Well, hey, and as always, first I was plans for more than you're going to, so I didn't get a chance to do my music example.
try to the
But,
10th power. Powers off real quick.
well, it'll probably take me a good 20 minutes. But let me just tell you guys really quick, if you want to read through what you have there, if you want to go ahead and just pin pan, I'll take 2 minutes and just give you a quick idea. To create a musical instrument like a piano or a guitar, you need to know a lot of math. It turns out that the relationship, now Jake's got an electronic keyboard here, but you guys have seen a grand piano, right? What's inside a grand piano?
Strings.
Strings, right? Just like a guitar has strings, and the strings are all different lengths. It turns out that the string lengths in a grand piano are related by an exponential function. And so when you think, you know what a grand piano looks like?
I have one.
You have one. Can you visualize that curve on the grand piano? Does it kind of look like that curve that we created there? Oh yeah, you know how that piano has that curve in it? The reason that that curve is shaped like that is because the piano string lengths are really an exponential equation. Each string length is about 95% of the one before it. So the longest string, you go about 95% to the next one, and about 95% again to the next one. And as you come down to those short strings, you keep on multiplying by 95%. And had we had another 20 minutes, I would have done that with you here today. That's what we actually brought the instruments in for. And I'm sorry I ran out of time. I wasn't quite sure how things were going to work today.
Are you going to be doing any more sessions?
I believe the last section is back with one of the astronauts back in the big room, which starts in about 12 minutes.
Can you just quickly tell us how that works, that math works with the guitar?
Absolutely.
Versus
Get
the
that.
95%.
Do you want to go ahead and grab that? Let me go back to my PowerPoint here really quick. You guys want to come down for a minute? I'm going to show you something. Can you guys take a measurement? Do you guys play piano at all?
I do.
Do you? Do you know how many notes there are in one octave on the piano? 8. 8 white keys, but also some black keys, right? There's actually 12 in one octave, and then notice how the 13th key starts it all over again. Okay, so there's 12 in one octave. You guys can each measure a guitar here, and what I want you to do is I want you to think of the open string like the first note. The first fret then would be the second note, the third note, fourth note, and so on. And I want you to count up to the 13th note. So
I'm wondering about the strings, why they do it like this, because these two are the same thing, these or these, unless they're
you have like the width of the strings, or
no, I'm talking about.
oh, how they come up here?
Yeah.
I think that's really just sort of a looks thing, so there's space enough to
14
tune up.
inches.
So let's see here. Well, what I want you to do first is I want you to count all the way up to it's actually the 12th fret, because that's the 13th note. So we're going to count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12.
15.
Now I want you to measure. When I pluck the string, it only vibrates from my finger down to here, right? I want you to measure the part that vibrates. So measure from that fret down to the bridge.
13.
About 13. Now measure the whole string from the nut to the bridge. Do it one more time. Was it 25?
22. 21.
25 and a half?
21 and a half.
Okay? What you should be seeing is approximately the one octave was about half as long as the whole string. And so that's the same thing in the grand piano. If you were to play notes on a piano an octave apart, the strings inside the piano, one would be twice as long as the other. And that's the same relationship that you see with the press on the top, is that when you cut the string length in half, you're up an octave. If you double the string length, you're down an octave. All right? So anyway, that's the fundamentals of it. Thank you guys all very much for coming today. Appreciate it. And I hope you enjoy, I think it's Colonel Wood who's addressing us here at the end of the day today.